Module 4.3, End Correction. So, thought that tubes open at both ends was easy. Turns out there's a slight little complication. If you remember when we did the Helmholtz resonator, when we calculated it just with the plain formula, it turned out that the frequency was lower than what we calculated. Well, it turns out that with a tube, we have the same issue that we had with the Helmholtz resonator. Because the molecules inside a tube are gas, we actually have to account for the extra air that's outside the tube. And so we have something that we call end correction. This is similar to effective length, and what that is you have to add 0.61 times the radius of the tube for each open end. So what does that mean? If L is the physical length, we then have to add 0.61 times the radius here and 0.61 of the radius there. And that's what we're going to call the acoustic length. So what does this mean? If the physical length is L, but the acoustic length is this, and we know that frequency equals V over 2L, if we account for the acoustic length, which is what is actually happening, what is going to happen to the frequency? As length increases, frequency decreases. So the frequency will be actually lower if we account for the acoustic length. And that's what really happens. The tube that is open at both ends has the frequency of a tube that would actually be a little bit longer because of the acoustic length. To review, to get an accurate calculated frequency for tubes with open ends, add 0.61 times the radius to the length for each open end. The length with end correction is called LEC, and it's also called the acoustic length.